In Calc 1, you learned to find the area under a curve. For instance, we have a function like this. Say this is your function. So this is y equals f of x. And you want to find the area under the curve from the point A to the point B. So this is in Calc 1. Let's call it in R2. Okay. So the area, call it A, this area A. It's the integral from A to B of f of x dx. All right, so if you have an area under a curve, you can express it as a single integral. We're going to extend this idea to R3. So that's what we're going to be doing in Calc 3. Now, assuming we have a function in R3, I'm gonna draw my usual go-to surface in R3 as the graph, and I'm going to this time I'm going to have my z-axis over here, and then I guess this would be that would be the x-axis, and this would be our y-axis. Okay, positive y-axis, positive x-axis, positive z-axis. I don't know why I'm drawing it this way, but I just feel like this might make more sense for what I'm trying to do. Okay, so if I want to find the volume of this function under the area, say we have a rectangular region, under the rectangular region, say from A to B, and then from C here to D. So this region is gonna cut across like this. All right. So let's call this region R. So we have a rectangular region that we call R. We're looking at it under this rectangular region. X, Y. Going from, on X, we're going from A to B, and then on Y, we're going from C to D. So this is the region R. Okay. So all we're doing is we're trying to find the volume of this curve, oh no, or the volume of this surface that is on top of this region R. Okay. So maybe something like this. So as you can see, it's not the whole surface, it's just the surface that sits on top of the region R. Just like here, we're not looking at the region, the area under the whole curve. We're just looking at the area from A to B. So in this case, we're looking at the area on top of the region R. I hope that makes sense. Okay. So this area, without going through a lot of rigorous proofs, this the volume, let's call this volume, let's call it V. Volume V that sits on top of R, volume V, is expressed as the integral, the double integral for the region of f of x, y, dA. So this is the notation for it. Remember, this is our function z equals f of xy. Okay. So the volume is this double integral. But how do you calculate this double integral? Since it's a rectangular region, the double integral is you're going from C to D, or let's do this. You're going from A to B. You know what? How about this? I'm going to go from C to D first. You're going from C to D, right, of f of xy dy. You're going to go dy first from C to D, and then you're going from A to B, dx. So it's double integral. You calculate the dy, and then you calculate dx. So this limit of integration goes with this dy, and then this limit of integration goes with dx. See that? All right. This is what we're going to focus on. Okay. Remember this region R, where the region R is a region xy such that x is between A and B and y is between C and D. All right. So we're going to be using this formulation to compute a lot of double integrals. So these are called double integrals. So this is a double integral. We're eventually going to look at triple integral, but let's start with double integrals. And this double integral is quite easy for now because it's a rectangular region. And you see what I'm saying down the line. Okay. And since it's a rectangular region, there is actually a fact that I have to state for you. This fact is called Fubinius Theorem. Fubinius Theorem says that if f of xy is continuous, then it doesn't matter the order we take for the integral. What do I mean? It means that integral f of x dA is just going to be the integral from, we can start with C to D and then do AB and then do dy dx, or we can actually also do C to D outside and then A to B inside fxy, then dx and dy. It doesn't matter as long as R is a rectangular region. This is because I'm going to put in parentheses here, as long as R is rectangular. Why? We're going to also encounter regions that are not rectangular. But if it's rectangular, it doesn't matter. Okay. Let us do some examples. Let's do examples. Go to the first one. Let's do the integral from 0 to 3 and then 1 to 2 of x squared y squared dy dx. Okay. All right, what is the region we're looking at? We're looking at a region like this. We're going from 1 to 2, 1 to 2 on the y-axis, and then we're going from 0 to 3 on the x-axis. So this is the region we're looking at. This is our region R. Okay. So we take the integral one after the other. So we do the integration with respect to x. When you're doing with respect to, with x, you're treating y as a constant. But actually, let's start with respect to y in this case because y is inside. All right, so we do the inside integral, the integral inside. That's this integral. So that will give us, it's with respect to y, so we just treat x as a constant. So we have x squared y cubed over 3. And then we're going from 1 to 2. And then we still have a 0 to 3 integral. And then we have dx. Okay. All right. So if we plug in 2 for y and we plug in 1 for y, we get 8x squared over 3 minus 1x squared over 3. Right? So plug in 2, we get 8, x squared over 3 minus 1x squared over 3, which is just 7x squared over 3, but and then we have dx. And then we keep going. This is integral 0, 3, 7x squared over 3 dx. Find the integral. So this is going to be 7x cubed over 9. We're going to go from 0 to 3. I hope I'm doing things right here, but if I'm not, you tell me in class. So you plug in 3. When you plug in 3, you get 27. 27 times 7 all over 9. Interesting. 27 times 7 over 9. So this is going to be 3. That's 21. Okay. I don't trust what I did, but I don't have anybody to help me. So let me just go through what I did and see if everything is correct. So I have, dy. So you plug in, so the first one here. Okay, so let's try the other way. So the answer I got is 21, but I was expecting some other answer. So I don't know how I ended up with 21. So let's see, 3, 2, 0. So you plug in 2, you get 8x squared over 3. Plug in 1. Oh, okay, that's fine. I have the x squared. Okay, that's good. All right, so let's try another problem. Or let's try it the other way. Because Fubinius Theorem tells us that it doesn't matter how we go, we're going to get the same answer. So let's assume, let's call this A. Call this A. How about B? Let's assume we go from 1 to 2 and then from 0 to 3. Same thing. dy dx. All right, so in this case, we do with x first. So we're going to get x cubed. No, x squared, not cubed. We're going to get x cubed over 3 times y squared, right? And then we're going to plug in 0. We're going to plug in 3. We're going from 1 to 2. 1 to 2, then dy. You plug in 3. You get 27 y squared over 3. You plug in 0, you get 0. So you now find the integral 1 to 2 dy of this same thing. So this is going to give you 27y cubed over 9. Plug in 1, plug in 2. So if you plug in 1, you get 20. If you plug in 2, you get 27 times 8 over 9 minus, you plug in 1, you get 27 over 9. Okay, so this is just 27 times 7 over 9, which is 21. Okay, the answer is correct. Answer and answer. Students love answers. I don't care about answers. I just want the procedure to be right. Okay, now I want to show you something. And I'm going to explain why. I'm going to show you something and I'm going to warn you on that thing. Okay? All right. So you see this integral we did? 1 to 2, 0 to 3, x squared, y squared, dy dx. I'm going to solve it in another way. I'm going to break it up. 1 to 2 of x squared. I'm going to put the x here, and then I'm going to write y squared 0 to 3. 0 to 3 dy. And I guarantee you, if you solve it this way, you're going to get the same answer. What do I mean? If you solve this, get an answer for it, and then solve this, get an answer for it, and multiply it, you're going to get 21. Now, the question is this. Why didn't I do this? Why didn't I just break it up this way? Break up the x part and break up the y part. Because in general, I can't do this. That's why I didn't break it up this way. In general, I can't do it. So for instance, if I had, say, the same integrals, 1 to 2, then 0 to 3, of tangent of x squared, y squared, dy dx. There's no way I could break it up. There's no way to break this up, you know. So you don't break things up. In general, you don't. You only break it up when you can separate the x and the y, because this is just the product of two variables, so you can easily separate them together. So if you have all the x terms in one function and you have all the y terms in one function and they multiply in each other, then you can break them up like this. Okay, so let's try another problem. So let's do this integral r y e to the xy dA, where r is equal to xy, such that x is between 0 and 1, and y is between 0 and natural log of 2. All right. And let's look at what we have. We're going to be looking for easy ways to do our problem. So assuming I start with the integral from 0 to natural log of 2 of y e to the xy dy, and then 0 to 1 of dx. Okay, now see, we have y e to the xy dy. We could do this first, and then do this later on. But realize what we're dealing with if we go this route. We're going to be doing integration by parts, which is fine. There's nothing wrong with integration by parts. But if we can avoid it, why not avoid it? So let's see if we can avoid it. Let's see if we switch up the integrals. If we make 0 to 1 y e to the xy dx first, and then go 0 to natural log of 2 of dy now. So if we go this route, integral with respect to x, in which case y is just a constant, then we are fine. We don't need to do any integration by parts. Okay, so I'm going to try this. Integration usually takes a little bit of time, so throughout this section, I might not, or this chapter, I might not be doing a whole lot of integration. I'll just set it up for you and let you do it. So let's do the first integral. So we have e to the xy, e to the xy. So if you find the integral of e to the xy with respect, if you find the antiderivative with respect to x, it's just going to be 1 over y, e to the xy, but you have y outside, so that 1 over y is going to cross out with a y, so you're left with just e to the xy, and then you're going from 0 to 1, okay? And then you still have 0 to natural log of 2 dy, okay? Let me save space. Go like this. So I'm going to put or here because we could either go this route or this route. So this is going to give you, if you plug in 0, plug in 1, you get, plug in 0, you get e to the y minus 1, okay? 0 to natural log of 2 dy. So take the integral, you get e to the y minus y. Then you plug in 0 and natural log of 2. When you plug in natural log of 2, you get 2. 2 minus natural log of 2. That's when you plug in natural log of 2. And when you plug in 0, you get 1 minus 0. You just get 1. Okay. So this gives you 1 minus natural log of 2. That's your answer. Okay. Now, we talked about double integral. How about we go ahead and just go a little nuts? Do triple integral. The same thing applies. So we're going from negative 2 to 2, integral 1 to 2, and then the integral 1 to e x y squared over z dz dx dy. Okay, so I want you to try this, okay, yourself. I want to see how you do it. Tell me the answer you got. Okay, so maybe I should do it. Why not? Why not? I still have some time. So if I start with z, I can do dz first, and then do dx and dy. Or I can use the fact, there's a fact I can use, two facts actually. The fact that this is a rectangular region. So what's the region we're dealing with here? The region of our integration. We're going from x, from maybe this is y, this is z, this is x. Okay. So we're going x from -2 or y from -2 to 2. -2 to 2. And then x from 1 to 2. From 1 to 2. So on the xy plane, we have this region. We have this. And then we can extend it from 1 to e on the z-axis. So something like that. I'm extending it from 0 to e, but you get it. I want to extend it from 1 to e. Maybe cut it off somewhere here. So we just end up with this part. But I'm just trying to show you that our region of integration is a cube. It's actually a cube, no longer just a rectangular region. But the same principle still applies, right? That you are able, Fubinius Theorem still apply. You're able to switch the integrals because all you have, the region is cube, meaning that all the limits of integration are constants. You realize that as we go further, you see that we're going to be dealing with limits of integration that are not necessarily constants, but these are constants. As long as they are constants, you can switch the integrals. Okay. Secondly, so that's the first thing we can use, first fact. The second fact is that we can use the fact that we can split this up, right? I can rewrite this integral. I can rewrite it, the integrand, I can rewrite this as x times 1 over z times y squared. A function of x, function of z, function of y. That makes our job easy. So that means we can go ahead and take the y integral by itself, isolate it. So the y integral is from -2 to 2, y squared dy. That is so easy. And then get the integral from 1 to 2 of x dx. Easy integral to calculate. And the integral from 1 to e of 1 over z dz. Easy integral to calculate. So I want you guys to try each of these integrals, get the answers, and multiply the three numbers. I want you to tell me in class how you did it. Okay, we're going to stop here.